Okay,
Gotcha.
so this is the second and final linear algebra review. And so last time we talked a little bit about how you can take a system of equations and convert that to a matrix. This is a good way to represent things. We talked a little bit about how a matrix can represent a transformation. We talked a little bit about what it means to be a basis, what it means to be spanning. You know, this is probably the only thing Manhattan beats Boston in, at least from my point of view. And so what we're going to talk about today is interpretations of what a matrix is. So if we have a system of equations, we could write it in matrix form, maybe as 2, 3, 4, 1, 8, 7, 3, 1, 4. X, Y, Z. And so here is some system of equations, and maybe we tell you we want it to equal 2, 0, 8. And then the question is, what are the choices of X, Y, and Z that solve this? So there's different techniques you can use to try to figure this out. We can also try to look at what this means. When we go through and we do the matrix multiplication, we get 2x plus 3y plus 4z equals 2, 1x plus 8y plus 7z equals 0, and 3x plus 1y plus 4z equals 8. There's another way we can view this. This is the same, and this is going to be extremely important when we do linear programming, as the vector 2, 1, 3 times x plus the vector 3, 8, 1 times y plus the vector 4, 7, 4 times z is the vector 2, 0, 8. And if you look at that, it's clear from looking at the system of equations that this is what's going on. And this is one way to view what a matrix does when it acts on a vector, or one way to view this way of writing it down. We're having a combination of the columns of the matrix. We have x times the first column, plus y times the second, plus z times the third equals this. And so we're asking, can we write this vector as a linear combination of these three directions? Okay, so this is going to be a very important advantage to have as we're going into linear programming. That when you take a matrix and act on a vector, all you get is a combination of the columns. And so in particular, if we look at different matrices, we can sometimes get a sense of whether or not there's a solution just by looking at what's going on. So I'll take a pretty straightforward one. If we look at this, is there a solution or no solution? No solution. Good. Why is there no solution?
0 plus 0.
Yeah, 0 plus 0 plus 0. The last entry here always has to be 0. There's no way it can equal 8. So what's really going on is we have the vector 2, 1, 0. We have the vector 3, 8, 0. And we have the vector 4, 7, 0. And so all we're doing is we're getting basically combinations of things in the plane. There's no way we can ever get a z component. Okay, let's do one a little bit more interesting now. Okay. So looking at this, hopefully it's not immediately clear if there's a solution. Right? Just looking at it, I can't immediately tell if there's a solution or not. But I'm very skeptical about the existence of a solution. So any thoughts as to why it's unlikely this has a solution? It might. But if I had to bet, I would bet no solution. So let's look. We have 2, 1, 4 as my first direction, right? Then we have 3, 8, 3 as my second direction. And then we have 5, 9, 7 as my third direction. this vector plus this vector equals this vector. Right? I don't have three different directions. So when I'm looking at the possibilities, this is going to give me a plane. Hello. So as a quick review, we're looking at the interpretations of what a matrix does when it acts on a vector. And what we said is, essentially when you have a matrix acting on a vector, the output is a linear combination of the columns. So in this situation, it's going to be x times the first column, plus y times the second column, plus z times the third column. So since I really only have two directions, I have a plane. So the probability of this point lying in that plane is 0. It might. You know, if I gave you the point 10, 18, 20, 10, 18, 19, 14, that would work. But if I choose a point at random, what's the odds that a point at random is in this plane? It's 0. Another way of writing this is the same as I can write, so we're going to use the following. Use 597 is 214 plus 383. So if I use that, this is the same as 214 x plus z plus 383 y plus z equals 208. And when we write it like this, even though we thought we had three variables, and even though it looked like we had a three-dimensional object, we really only have a two-dimensional object. I can make this number anything I want, I can make this number anything I want. And I can do that in many ways. So if there's a solution, there'll be infinitely many solutions, because I can keep tweaking these numbers. I can make z anything I want, and then adjust x and y. So, if a solution, infinitely many solutions. If there's no solution, there's no solution. And you would expect that there are no solutions. So, obviously this matrix was not chosen at random. Right? I was deliberately adding to make the last column the sum of the previous two. If you were to choose a matrix at random, a 3 by 3 matrix at random, do you think it's likely or unlikely that you would have some kind of combination of these vectors? So you're shaking your head, so you're thinking it's very unlikely. Right? You have to work. One of my favorite examples is the following matrix: 1, 2, 3, 4, 5, 6, 7, 8, 9. You know, if you're ever teaching a linear algebra class, or well, I am, this is a good thing to try, right? Just put down the numbers in order. The first plus the third is twice the middle. As a nice exercise, if you take the numbers 1, 2, up to n, down to n squared, if n is greater than or equal to 2, greater than or equal to 3, you have dependence. So we want a nice way to tell if these vectors are all in different directions. Another way of saying this is we want a way to tell if these vectors span R3 or in general span Rn. So the problem is, if I don't have 3 independent directions, I'm in trouble. And so right now I'll start by doing things in either R2 or R3, and then we'll expand up and say a few words about the general case. So the quest for independence. And so we're going to assume a few facts from linear algebra. So Rn is the set of all points x1 through xn each xi is real. This is an n-dimensional vector space. The standard basis is E1 through En, where E1 is 1, and then all zeros, En at the bottom is zeros, and then 1. So basically the EIs have 1 in the ith direction, and 0 everywhere else. If you had to ask for a nice space, this is the nicest space you could ask for. Right? You know, the number 314, vector 314 would be 3E1 plus E2 plus 4E3. And I can write anything in terms of these basis vectors. The question is, are there other basis vectors we could use? And so, a big result of linear algebra says that all bases of a finite dimensional vector space have the same number of components, have the same number of elements in their set. And so remember, to be a basis you need two things. You need to span, so everything in the space can be written as a combination. And you need to be minimal. It's not possible to have a smaller sized set work. So here's a non-standard basis. E1 plus E2, E2, E3, En. And the reason that this will also work is it's almost the same as the original basis. I've only changed the first one. Well, all I have to do is, if before I needed one copy of this, now I would have 0 copies if I had one of them. So for instance, now if I want to write 314, I have to have 3 E1s. But now that gives me a 3 over here. I only wanted a 1, so I'm going to have to subtract off 2 E2s, and then have 4 E3s. And so I can just correct for the extra copies of E2 I get from here by just jiggling this a little bit. Okay. So now, we want to have a basis. So, say V1 through Vn is the basis of Rn. So this is going to mean two things. One, any V in Rn is the sum AI, VI, items from 1 to n for some real values in I. And two, basically, this is the spanning line. Our set is of minimal size. It looks a little foolish to say this, but really n equals n. So I could write instead, say V1 through Vm is a basis of Rn if this works, and then m equals n, that the number of vectors I have is equal to Rn. Just in the, we've seen this so many times that it's natural to just write now, we have to take n components, we have to take n vectors. We're not going to have more than n vectors. So let's imagine we have a basis. So this is what it means to have a basis. You're spanning the things that are linearly independent. So one nice thing is the representation is unique. And so why? Assume the sum of AI VI equals the sum of BI VI. Well, if that's true, then this is the same as the sum, I goes from 1 to n, of AI minus BI times VI equals 0. And so now, if one of these numbers here is non-zero, you could write that vector in terms of the others, which means you wouldn't need it for linear combinations, which means you could do this with fewer vectors. So if a1 minus b1, for instance, is not equal to 0, you get v1 is 1 over a1 minus b1, negative 1, sum I equals from 2 to n of ai minus bi. And then you wouldn't need v1. Every time you see a v1, you could replace it with the combinations of v2 through vn. So one very nice thing about a basis is you have a unique way of writing things in terms of that basis. So if you want to write the number 314 in decimal, there's only one way to do it. It's 314. You could write the number 314 in a different way in a new basis, in binary. Because there you're using a different basis. Rather than using powers of 10, we're now using powers of 2. Instead of using the vectors v1 through vn, maybe I use a new basis, w1 through wn. And then I would probably have a different way of writing my vector, with different coefficients ai. So if you really want to annoy people, ai is a function of your basis. Have some extremely painful notation, right? It's not really worth keeping track of it, but these coefficients really are a function of your basis. Different basis, choices will give you different coefficients. Okay, so if we have a basis, we can write any vector uniquely as a linear combination. This has profound applications for solving systems of equations. So what is the relation between this? So let's keep this one line on the blackboard, because we need the space. So assume we have the following equation. I'm going to make a matrix. The first column is going to be v1. The second column is going to be v2. And then the last column is vn. And then I want to solve x1, xn equals b1, bn. And again, if I give you any matrix, I can clearly regard the matrix as a bunch of columns. And each column is a different vector. This is the same as trying to solve this problem. x1 times v1 plus x2 times v2 plus xn times vn equals our vector b. Well, that's what we were just talking about a moment ago. Because the v's are a basis, there's a unique solution. As the vi's are a basis, we have a unique solution. Now notice right now I'm not telling you how to find the unique solution. This is theoretical mathematics, right? A solution exists, the solution is unique. In practice, of course, you would want to find the solution. Gaussian elimination is a great way to find the solution, a great way to go through the algebra in a clear way. But the important thing for us is that a solution will exist and it will be unique. So this is what happens in the case when the v's are a basis. Let's assume now that, say, v1 through vn, instead of being a basis, are in Rn. So they may or may not be a basis. So now when we're trying to solve this equation, this matrix equation is the same as this. And now it all comes down to is whether or not B is a linear combination of the V's. So there's a solution if and only if B is a linear combination of the VI's. To some extent, all we've done is basically just rephrased what we have. There's a solution if and only if B is a linear combination of the VI's. Well, is that really any different than just writing it like this? It's more of an emphasis point here. as to what's really going on at a fundamental level. When can you solve a system of equations like this? When the outcome is a combination of the columns. And so what's going to really matter is how many independent columns do you have. If this is a basis, then you'll always be able to solve. If it's not a basis, you'll have trouble. Everything we're doing right now is for a square matrix. If I give you a non-square matrix, the same thing will hold. And so, for instance, let's look at a few examples with some non-square matrices. All right, 1, 2, 3, 4, 5, 6, 7, I think. x1, x7 equals pi e. Okay. Do you expect to have a solution to this? So do you expect to be able to solve this massive system of equations? And if so, do you expect to be able to solve it in many ways or just one way? So here, our vector v1 would be 1, 2. Our vector v2 would be 3, 4. And then v7 would be 4, 8. So are these vectors independent? No, we have 7 vectors in R2. Can't be independent. 7 vectors in R2 are not independent. So if there's a solution, there will actually be infinitely many solutions. So if solution, infinitely many solutions. So all we have to do is find one solution. So clearly we have some issues. The vector 1, 2 is actually in the same direction as the vector 4, 8. So the question is, do these vectors span the entire plane, or do they just span a line in the plane? If we start looking, here's the vector 1, 2. So is every vector in the same direction as 1, 2? No. We've got, for instance, the vector 0, 1. If we go up to here, it would be 0, 1. So these two vectors are clearly independent. And so if you want to write a general point, x, y, as some multiple of 1, 2, and some multiple of 0, 1, well, A is easy. A has to be x, because this can't give you anything. So you basically add as many copies of this as you need to get x, and then you use this to fix the y component. So A would have to equal x, and then you would get y equals 2x plus b, therefore b is equal to y minus 2x. And so that would give you a way to solve this problem. So it's an interesting question, except for 1, 2, and 4, 8, is everything always in a different direction than everything else? I believe so. I believe that's the only time we actually have 2 vectors in the same direction. So there's going to be lots of different ways of writing pi and e for the choices of x1 through x7. All right. Let's make the problem a lot easier. Okay. So now in a situation like this, it's clear there's no solutions. So if there was a solution, there would be infinitely many, but sadly in this case there are no solutions. Okay, so here, no solution. I'll pause for the camera for 3 seconds. Alright, so now instead of 0, let's make that a 10. Solution or no solution? Yeah, now there's going to be solutions. This one, you choose what you would take pi times of this, and then you can take, you would take e over 10 of these. and then you'll use any one of these to correct. Now, if you look at this, one of the vectors is bad. One of the columns.
6.
Yeah, the sixth column is quite bad, because it's 0, 0. So what it's telling you is, no matter what value of x6 you put in, it's going to make no difference. It's not going to affect what you can get. So what we've hopefully seen is that in trying to find out whether or not there's a solution, it really comes down to how many independent columns do you have, what's the space they span, and is your target in that space. So for square matrices, there's an easy way to check. So square matrices, you can check for independence easily. So does anyone know the way to check and see if the columns of a matrix, of a square matrix, are independent? There's a very nice number associated with the matrix. So there's not that many numbers you can associate with the matrix. So if you remember eigenvalues, you use this function, use this when you're looking at eigenvalues. It's the determinant of a matrix. So there's a huge theory that's devoted to determinants. And so I'm going to start off by just doing the determinants in the plane, and then basically click my heels and say that the stuff generalizes. Okay. So let's take a matrix A, B, C, D. You can view this as a function of the columns or a function of the rows, doesn't matter which perspective you take. Let's graph things. And this is where it might have been a good idea to thought a little bit more about, but we'll see how much we can get. So here, let's say this is the vector AC. And let's say this is the vector BD. And so basically, I can convert this to a parallelogram. And so this parallelogram is I take a multiple of AC, and that multiple is going to be something between 0 and 1. And I take a multiple of this, and that's going to be between 0 and 1, and I add them. So if I just take one multiple of AC on here, if I take half a multiple on here, a quarter multiple on here. If I take a full multiple of this and a half multiple of this on here, a half multiple of each, and I'm at the center. So this is the parallelogram. If the two vectors are in the same direction, the parallelogram is going to look very different. The parallelogram would look like this if in the same direction. So there's a very nice way to tell if the two vectors are in the same direction or not. Compute the area of the parallelogram. Right? If the area is 0, they're parallel. If the area is not 0, they're independent. So, area of parallelogram says if parallel, area equals 0, or independent, area does not equal 0. One of the things that's very nice about this is we don't need to calculate the determinant exactly, right? All we need to be able to tell is 0 or non-zero. Now, the value of the determinant might actually tell us something else. Maybe if the determinant is very small, maybe the two vectors are very close to being parallel. Of course, another thing that matters is the size of the vectors. If I double the size of this, I'm going to double the area. Okay, so the question is, how do you calculate the area of a parallelogram? Well, one way is base times height. And so this is where you now have to start remembering from trig and some of the other stuff from linear algebra. I can call theta here. Okay. And so now, the length of this times the sine of theta is the height. Right? So height is the length of this, which is the square root of b squared plus d squared times the sine of theta. The base is the square root of a squared plus c squared. So I'm just using Pythagoras. You know, I have a vector. The length of the vector is the square root of the sum of the squares. Alright, so we can combine these and we can get the area. So we get area of the parallelogram is the square root of b squared plus d squared, square root of a squared plus c squared times the sine of theta. Now, unfortunately, the sine of theta is not immediately apparent in terms of a, b, c, and d. I want a nice formula for the sine of theta. There's also something else that should be a little bit annoying about this. What don't you like about this equation? What does it involve that's annoying? Square roots. So rather than studying the area, what should we study? Area squared. Right? If we study the area squared, oh, this is much nicer. Right? And you know, it's very easy to figure out, you know, the area squared is non-zero, but only if the area is non-zero. Okay, now we have sine squared. As soon as you see sine squared, what should be going through your mind? Do you know any relations involving sine squared?
Something about the triangular root.
So what's the big thing involving sine squared? So this is the Pythagorean theorem. Right? Sine squared plus...
Sine squared equals to 1.
So this is the same as a squared plus c squared, b squared plus d squared, cosine, I'm sorry, 1 minus cosine squared of theta. Now, of course, you should be asking, why would we replace sine squared with 1 minus cosine squared?
Because the square cosine theta can be something.
Yes, so cosine theta has a nice answer in terms of all of this. What is cosine theta?
2.
So this is where you need to remember some linear algebra. If I give you two vectors, the dot product of v dot w is the length of v times the length of w times the cosine of the angle. So the dot product squared divided by the length of v squared times the length of w squared is cosine squared of theta. So this is a very useful relation. And in fact, this is what was motivating the switch from here to here. Is cosine is actually well defined in terms of the intrinsic quantities we care about, a, b, c, d. Sine is not. And so using this, okay, we can now substitute. Here, my vector v is ac, my vector w is bd. Oh, beautiful, look, that's length of v squared, length of w squared, right? That's going to cancel with the stuff down here. And so we'll get a squared plus c squared, b squared plus d squared times 1, and then minus, this hits down here, so that cancels, so I get v dot w squared. The dot product of two vectors, v dot w, is a times b plus c times d. You multiply the first two components, multiply the second two components, and add. And so in general, if I had three components, I would multiply component by component and then add. You can define almost anything in mathematics. This is a good thing to define. And the reason is this dot product turns out to be related to geometry. So I'm not going to get into right now why this is true. If people haven't seen this and are interested, I have some handouts or some links I can give you. So this is now going to be minus a AD plus CD squared. And if you do some algebra, this is the same as AD minus BC squared. So one way to prove this, of course, is to expand this out, and subtract. And then this is where the miracle occurs, and you see that the two expressions are the same. So the question is, can we just look at this and see that this is reasonable? Well, I'm going to get an a squared b squared when this hits itself. Oh, I have an a squared b squared, those will cancel. A c squared d squared, that will cancel.
B squared, C squared.
So b squared, c squared.
A squared, D squared.
And great, that will be over here. A squared, d squared, that will be here. Then the cross term is going to be negative here, and I'm going to get negative here. I'll have a, b, c, d. Perfect. So this is the determinant of a 2 by 2 matrix, AD minus BC. And so the signed area is AD minus BC, and we call that the determinant of A. And so A times D minus B times C, that's the determinant of A. It's a quick and easy way to tell if the matrix is, if the vectors are linearly independent. And it makes sense, if the two vectors are in the same direction, the area of the parallelogram will be 0. If they're in different directions, the area will be non-zero. It turns out that there's a way to generalize the determinant to 3 by 3 and higher dimensions. And the resulting determinant will tell you whether or not the vectors are linearly independent. In 3 dimensions, it'll be the volume of the parallel pipe head. And then it gets a little bit more complicated to say just exactly what it is, but it's the volume or the hypervolume of the region spanned by these different directions. And so, if I give you a matrix, one way to tell if the columns are independent is to take the determinant. Or similarly, you take the transpose, and then that will tell you whether or not the rows are independent. Okay. So, a few more facts about matrices. So let's say I give you a M by N matrix. So we have N rows, we have N columns. So maybe for definiteness, we have 3 rows. Let's say we have 30 rows and 4 columns. Okay? So the question is, I have 30 rows and I have only 4 columns. What's the largest the dimension of the column space could be? The dimension of the linear combination of the columns. Dimension of linear combination of columns is at most what? So I have 30 rows and 4 columns. Best possible case, what could be the dimension of the result? The dimension of the column space, the linear combination of columns. So it's going to be something like, I'll have x1 v1 plus x and 4 v4. So what's the largest it could be? 4. Even though I have 30 rows, even though these are vectors with 30 components, I can't get a 30-dimensional column space because I only have 4 directions. Okay? So even though I have 30 rows, even though these are vectors in R40, in R30, it's still at best 4 directions. Okay. Now let's do it another way. Now let's say we have 4 and 30. So now we have 30 columns. So now here, each VI is in R4, and we have 30 of them. Okay? what's the largest the dimension of the column space could be? 4. Right? Because it doesn't matter that I have 30 of them. They live inside R4. I have at most 4 directions in R4. There's a nice way of writing this number 4. It's the minimum of 4 and 30. And so this gives you a sense of what kind of spaces these columns can give you. And so then the last thing to mention, I think, for today is what would happen for generic matrix. So a generic n by n matrix. So I choose n vectors at random in some sense, and you have to, of course, define what at random means. And I put them into a matrix, and I ask, is that matrix going to have non-zero determinant? Will the vectors be independent? Well, let's imagine we're in n equals 2. So we start off, and we choose a vector. Now we need to choose one more vector. So if you want, think of it as, without loss of generality, all your vectors have unit length. You can rescale the vectors. So we have to choose an angle. What's the probability we choose the angle either the same or 180 off?
Almost 0.
Almost 0, right? And so with basically probability 1, our next vector would be in a different direction. And similarly, if I try to go to 3 dimensions, I now have 3 vectors. If I choose 3 vectors in the plane, of course, they're going to be linearly dependent. But if I'm now choosing 3 vectors in 3-dimensional space, it's very unlikely that my third vector is going to lie in the plane that the first 2 span. And then in 4 dimensions, it's very unlikely the fourth vector will lie in the 3-dimensional hyperplane the first 3 span. So the way you should look at it is basically probability 1 that a random n by n matrix has n independent images. If you don't have n independent directions, vectors, columns. If you don't, that means one of your vectors lies in a lower dimensional subspace. If you tweak one of its components by just a little bit, that should be enough to push you out. So if I happen to choose 3 vectors that all lie in a plane, if I add just a little bit to one of them, that should push me out of the plane and back into 3-dimensional space. So there's a lot of fun questions you can ask. A really good challenge is write down an n by n matrix with n independent columns. This is the closest I ever came to wanting to hurt one of my colleagues. Years ago when I was teaching, this was an exam question in the linear algebra class I was grading. And the direction said, write down a matrix. Well, almost any matrix you write down is correct, which meant that as graders, we had to check and make sure it worked. And essentially everything that people write will be correct for this. You have to really work hard to not write down something that works. That's a bad word. Or you need to add and prove it works. Now it's more interesting. Can you come up with a constructive way to write down a matrix such that it will work? Almost any matrix you write down will work, but can you do it in a constructive manner? there's a really nice generalization. You can take n rows and infinitely many columns, and you can fill in a matrix such that any n columns are independent. It turns out, again, almost any choice of matrix will work. But there's an explicit procedure that allows you to do this, so that no matter which columns you choose, it will be independent. This is going to be extremely important for us when we do linear programming. When we're trying to find solutions or prove solutions exist, we're going to be concerned with we have a matrix, and we're going to be looking at a subset of the matrix, looking at just certain columns, and asking what's the space that these columns span. And so I guess the last thing, since we still have 1 minute to go, is let's say I'm going to just give you one bit of probability background or combinatorics background. And so we have a n by m matrix. Have I been doing n by n? I've been doing n by n, I think.
M by N.
n by n matrix. So we have m rows, we have n columns. And so what I want to do is, how many ways are there to choose k of the n columns? Or it doesn't matter. So how many ways are there to do that? So I have n columns, and I want to choose k of the n columns.
Just any K.
I'm sorry?
Just any K, no need for independence.
No need for independence. I just want to know, for instance, maybe I have 3 rows and 4 columns, and maybe k equals 2. How many ways are there to choose 2 columns from 4?
4 choose 2.
4 choose 2. And in general, it's going to be n choose k, which is n factorial over k factorial and minus k factorial. For linear programming, we will need to know that there is some number. The actual value of the number will then tell you how long something takes. But I think we all agree that if you only have finitely many columns, there are only finitely many ways to choose k columns from n. What that finite number is, I don't know. But it's a finite number. Okay, well, I do know what's this. Okay, so starting next Wednesday, we will then move into actually linear programming. And I'll start off by explaining, here are a couple of problems that linear algebra solves, and here are some possible generalizations. And one of the generalizations is linear programming, and then we'll actually start seeing what problems we can solve.